questions? Okay, so I encourage you again to stop me anytime. Okay, just let me know. If you have any question, you can contact me by email. If you don't have my, well, you should have it from the slides. Anyway, you can always reach me through the course coordinator, Professor Suvas Kardas. Okay, and yeah, I'm available, after the lectures for more clarifications. And normally, I mean, except for today, because we have another IEEE lecture at 4, the designated time for interaction, official designated time is 4 to 5 in my office, which is close to Professor De Barati's office. So anyway, you can pop in also other times, and during the class and after the class. So I want it to be very informal, as much as possible, more of a discussion really. So yesterday we saw basically what it means to talk about 5G, right? So what is different, what is same to some extent compared to former generations, right, of cellular systems. We saw that a big differentiating factor is that now the requirements are much broader. The requirement set is much broader than it was, for example, for 4G, right? It's not just about data rate anymore. It's about reliability. It's about delay. It's about, I would say, a more general definition of quality of experience. We also encountered the definition of service-aware networks, as opposed to the traditional way to do networking, which was network-aware services, which means we move more into something like that is user-centric rather than best effort based on the network. So not so network-centric anymore, but user-centric. So the network as an enabler to satisfy the wishes of the users. Okay. We saw another big thing that changes compared to 4G is that there is a much tighter integration with other technologies, right, and other networks, so to speak. So it's not anymore just the broadband, right, the mobile broadband like LTE, LTE Advanced, but we also see that we try to integrate the design of the network with other services like Wi-Fi and all sort of machine type communication, right? That wasn't there in 4G, definitely. Now, to get there, we need different technologies, right? There is not one size fits all technology, right? We need to see what is needed. So eventually, the three main leverages you have to improve the capacity of a network are either you increase the spectrum available, or you increase the spectral efficiency, of a link, or you increase the density, of the deployment. These are the three main categories. Now, within these general categories, you have a few sub categories, but just to give some examples, increasing the spectrum, that's what cognitive radio is all about. That's what new forms of spectrum sharing are all about, like license shared access, the PICAS framework, SAS framework in US, ASA, like this authorized shared access, LTE unlicensed, so the LTE operation in Wi-Fi bands, even like integration with Wi-Fi if you want, is sort of getting more spectrum, right? Why do we care? Because of the Shannon equation, right? So the bandwidth multiplies, so the bandwidth is a linear factor, right, of the increase in the capacity. So up to some extent, we know that if you go too high with the bandwidth used, noise kicks in. But let's say, at least for some reasonable region of bandwidth, you have a linear increase, right, of the capacity with the bandwidth. So that's why we do it. The second and the third actually categories, so increasing the link efficiency and increasing the deployment density, have more to do with what is inside the logarithm of the Shannon equation, right? This SNR, SINR. So, for example, I mean that, and also something that multiplies the logarithm outside. So for example, when you do MIMO, if you do things like spatial multiplexing, you would have again a linear factor. So you would multiply, say, the minimum of between the number of transmit and receive antennas times the bandwidth times the logarithm. So again, up to some extent, you still have a linear increase. Or if you do things like beamforming, you would increase the SNR. So it's something that is of a logarithmic nature, right? Not linear, still helps. Now, when you increase the deployment density, you are playing again with the argument of the logarithm, because essentially, well, that, and also I would say probably the bandwidth. Basically, you are trying to increase the spectrum reuse. So there is a bit to do with increasing the bandwidth available, but there is also a bit to do with increasing the received signal power, right? Because you are closer. So if you are in a denser network, it means that on average, transmitter and receiver will be closer, right? That's the idea behind HETnet or small cells networks. There was a prediction from Martin Cooper, who is considered by many the father of mobile cellular technology. You know, not a prediction, but like some sort of analysis about the increase of the wireless data rate for the past 50, 60 years. Okay, so what turns out to be the case is that the technologies that so much we focus on, like MIMO, OFDM, coding, they don't contribute an awful lot. Okay, they do, because the gains are multiplicative. So they do contribute, let's say, for a factor of 5 to 10, more or less. And things like, you know, getting new spectrum, being more efficient in the multiplexing, like OFDM, or you know, new things like filter bank or GFDM. These sort of things again don't contribute an awful lot. Another factor of that order. Okay. So what really plays a huge role is the third category I mentioned before, is the densification of the network. So if you look, let's say in the past 50 years more or less, the wireless data rate available to us has increased of by a million-fold. So 10 to the 6. Of these, 1,000 has been due to densification of the network. Okay, so making cells smaller. So basically, it means that, you know, if you combine MIMO and anything else, more or less, we have been doing at Phi and, you know, even Mac, that would account for the same as the densification. So the densification alone counts as everything else. Okay, I'm not saying that you don't have to do everything else. I'm just saying that you also have to have a perspective what matters most, right? So you still need the gains from MIMO, from spectrum sharing, from multiplexing, and all of that. But I think eventually you cannot beat the fact that if you're closer to the transmitter, you get a better signal. That's physics, okay? So eventually it's path loss. So we have to be keeping that in mind when we design the next network. That's why a lot of focus, as Kartik and other guys I know the research they're involved with, they do work. There is a lot of work going on in ultra-dense networks, HETnet, small cells, and it's not by mistake. It's because it's very, very important. Okay, so that's just a brief recap. I want to quickly go through again the technologies that are of relevance to 5G. And so if you focus, for example, on the spectrum category, okay, of increase to the capacity, I was mentioning before, millimeter wave is a very natural choice. There is a lot of fallow spectrum, okay, if you go high up in frequency. High up, I mean, roughly speaking, beyond 28 gigahertz. Okay, depends on the definition, but definitely at least an order of magnitude higher carrier frequencies than we are used to. Okay, normally we work around 2 to 3 gigahertz. Some exception is the Wi-Fi band at 5, some radar bands at 5, but in the main, what they call the sweet spot for wireless communication is between few hundreds of megahertz, probably from 400 up to 6 gigahertz, I would say, right? Some people even restrict it to up to 3 gigahertz, but So it's in this region. Now the problem with that is because it's a good part of the spectrum, everything is using it, right? From Wi-Fi to Bluetooth to LTE to WiMAX to you name it. Okay, so all of these technologies are using and it's what is called also like the 2.4 band, for example, is called industrial, scientific, and medical. So it's not just telecom, right? It's all of these appliances from medical sector, from industrial sector, that they use this band. So there is a lot of interference practically, okay? A lot of congestion. Now people have been working out solutions, of course, like the cognitive radio is all about making better arrangements, right, between coexisting systems, and we have been trying to do handoff between cellular to Wi-Fi, and there are studies even in my group about coexisting with radar systems, right? So we are trying to get the best out of this sweet spot, but it is a limited region of the spectrum nonetheless. Okay, there is only so much you can do. So eventually a natural solution is to go into uncharted territories, right? No, unexplored. It's like in the past when it became like too many people living in a certain space, they would move, right? They would migrate and conquer new lands, and the same thing here. So now the good thing about there are some good things, some bad things about millimeter wave. The good thing is that there is a lot of spectrum. Okay, so we're talking like swathes of gigahertz, few gigahertz actually spectrum, which is 10, 20 times higher than the spectrum we have today. Again, think about the Shannon equation. You multiply, right? So if today we have a gigabit per second, if you go to millimeter wave, you can go high, very high, right, up to 50, because of the band. There are some catches though, of course. This propagation, it's somehow limited, right? So that you cannot go that far with the signal at millimeter wave, because we know that we know from physics that the higher the frequency, the shorter is the range of your signal. It attenuates faster with distance. Other complications are that the technology is costly, right? It's difficult. The higher you are in frequency, the more difficult it is for your RF, and sampling rate, and so everything gets more complicated, right? Eventually, a lot boils down to what carrier you're using. So the higher the carrier, the more difficult it is to operate your system, right? I'm not an RF engineer, but I know it's kind of a nightmare for them to design these systems. What can you do to combat the basically this limited propagation and to be still efficient in your transmission? It's kind of a default assumption that when you have millimeter wave, you have beamforming. Okay, you do have to have some MIMO system doing beamforming, because the limited power you have at the transmitter has to be really well used. Okay, so it's not like that you can be squandering it like you do at lower frequencies, where it doesn't matter because the signal propagates naturally far. Here you have to be more conservative, right? So you do need to basically transmit directionally. So there is a problem with user tracking, right? You have to keep tracking the user when they move, while, for example, if you work at lower frequencies, it doesn't matter really, right? You reach the user within a radius. Here it's more like within a small sector actually. Okay. And then there are RF complications, and I mean what I know of millimeter wave bands, they are also very susceptible to line of sight blockage. They are not at all exploiting the multipath phenomenon. As the lower frequencies, much more you have to really see the user, I mean electromagnetically see the user and transmit to the user. So you cannot exploit reflections, right? Because anything else will kind of be too basically weak by the time it reaches the receiver. Okay, so, and for example, it's very sensitive to user body orientation. So if now I'm communicating with my millimeter wave access point, and then I turn a bit, as you normally do when you talk right on the phone. I mean, I think a common thing is that you start to move around a bit. That's fine, of course. We are not like statues. The problem though is that if you start to do that with millimeter wave beyond some angle, you lose the signal altogether. So there are experiments showing, for example, that if, say, you have a chest-worn antenna, okay, you put the antenna here, you communicate with another person and you face each other, signal is good. As soon as somebody turns, then the signal is lost altogether. That wouldn't happen at lower frequencies. Okay, so there are some challenges that are definitely specific to millimeter wave. We do have a project in Trinity College in collaboration with University in Northern Ireland in Belfast and Virginia Tech, studying actually these aspects and especially the implications these have when you do resource allocation and when you do system level design. So there's been a lot of work in physical layer, channel modeling and so on, but much less work about the implications of these new spectrum bands in terms of how you run your network, okay, how you design your system. So that's something we are doing at the moment. Any questions so far? Nope. Okay, small cells, we go back to the category 3 I was mentioning before. So you need to densify the network to get a better use of the spectrum and to get a better SNR, basically a SNR. What are the catches here? So the catches are that the closer you get, since the closer you get to other transmitters, I mean, you get closer to your receiver, but since everybody is kind of, it's like if you think about it, like the universe, like expanding, or so now we are in the expansion phase. But if you reverse that, you would see things getting closer and closer, right? So if I'm closer to my receiver, it means I'm also closer, to their receivers, to their transmitters. I mean, the opponents, right? So interference is a big deal. Okay, so in fact, let's say normally you do design cellular networks for, let's say, the macro cellular networks, assuming that noise is the limitation, right? The more far away you are, the more you have problems. So you do design the cell size in a way so that the SNR is good enough at the edge. Here there is, in a sense, no edge. Okay, there is no edge problem. It is that the cells are so small that that's not the problem anymore. So the problem is much more of an interference nature. So these are interference limited systems, and it changes the tractation altogether, because if noise is the main factor, then you can do some things. Okay, so say power control, or you can have maybe more powerful yeah, you probably need also to kind of, I think power control will be probably the main thing you would do. Instead, if you have interference, then you need even more than in cellular networks to decide which channels are allocated to the different small cells. Okay. Yeah, so I don't think the power control is really going to help too much in this case. It's more, in a sense, a problem of deciding which frequency each base station should use, and since you have so many options within the range of the user, it kind of, as I said yesterday, reverses the problem of scheduling. In the normal scheduling problem, you would pick the users you have to serve with one base station. Here, in a sense, you have to pick the base stations you want to be served. You have to be served from, right? So it's kind of dual, if you want, of the scheduling we had in 4G. Now, I will have a few lectures on this, so I will not spend an awful lot of time, but just to tell, there is a lot of work going on in waveform design. Now, one interesting thing that I noticed, well, not only me, a few people noticed in former generations, is that there has always been sort of a competition between two contender technologies, and then one made it and one was abandoned, was like put on standby, say. So, for example, in 4G, there was, OFDM and other, let's say, possible alternatives. So it would have been, say, I think, multi-carrier CDMA, possible evolutions of CDMA, and eventually OFDM was chosen as the reference access scheme. In 3G, the lucky guy was CDMA, right? And so on. Now in 5G, I kind of think that's probably not going to be the case. I mean, I don't believe that there is going to be one access technique that will just, you know, eat up all the cake. I don't think so. And why don't I think so? It's because of what I said yesterday, the heterogeneity of what we are trying to achieve. We know that OFDM is good for some things, but it won't be good for others. And the same goes with alternative waveforms. So eventually, there is likely going to be a pool of waveforms you can pick from, right? And what you pick depends on the requirements. So if you have a scenario where density is moderate and in a sense synchronization is not so difficult to enforce, OFDM is okay. If you have a scenario where the density starts to really, you know, increase a lot, and therefore synchronization becomes an issue, to enable the synchronization of all these devices is going to be very problematic, then you need something else. You need to relax, in a sense, the synchronization requirements, so the orthogonality that you have in OFDM. Okay, so you cannot use OFDM for this kind of dense networks, say sensor networks, very dense deployments of small cells. I believe you need something of a different nature. So possible candidates are GFDM, generalized frequency division multiplexing, FBMC, filter bank multi-carrier, UFMC, universal filter multi-carrier, and there are others. Okay, these are the three main ones as far as I'm aware. They all have pros and cons. In essence, what they do, they try to actually push the out of band emission down. Okay, so what does it mean? It means that, you know, basically what you do with OFDM, you filter. You don't filter really things. In time, you basically have a rectangle. Okay, that's the pulse shape you use in OFDM. What that implies, if you take the Fourier transform, what this implies, if you take the Fourier transform, that this decays slowly. Actually, decays with 1/f. Okay, so it's a sink. It does decay fairly slowly. Then, if you remember from your DSP classes or, you know, basic digital comm classes, you probably remember something like this. So anybody that has some idea, try to switch it off maybe. Sorry. Okay, so basically you will probably remember this relation between the pulse shaping and the decaying frequency. So if say to do a rectangle, it's like to multiply by 1, basically, right, in time. So you do nothing practically. That's the problem with OFDM. So some people have been trying to filter things in OFDM. Some people have tried to change the signal structure altogether of modulation and demodulation. We're going to see more of that later this week and beginning of next week. So I'm asking now, especially to the phi savvy people in the room, what could you do if the rectangular pulse shape doesn't work? What is the natural thing you would do as a DSP engineer? If that's not good, so what could you do instead? Anybody? Sashank must know that. Yes, you do pulse shaping. Practically, what does it mean? So instead of using a rectangle, what could you use, for example? That's right. That's the natural option, right? You can do other things, but raised cosine is the first thing I would pick, right? So what happens then is that the decay in frequency gets quicker, right? So for example, if you have raised cosine, I think the decay is 1 over f squared, right? So you definitely decay much faster, okay? So in essence, that's what they try to do. There is also something to do with the signal structure, you know, how you play with guard times, what we call OFDM, cyclic prefix in OFDM, and then they try to basically either minimize the use of guard times or remove it altogether, right? To also to basically enable short delays, right? You want to process things faster in some applications in 5G, so OFDM again is not too good for that, because every now and then you need to have this, with this cyclic prefix, you basically, first of all, you're wasting spectral efficiency, right? Because some of your transmission time is not going to be used for useful data transmission, right? Though it has good properties against ISI and enabling an easy way to convolve in frequency, right? Signal and the transmit signal in channel, but in essence, it's not a useful part of your frame. And then they try, you know, to cope with that, either limiting the time, you know, you use for your guard time, or removing it altogether. You have other problems, okay? It's not that it's freelance. For example, in filter bank, you have a ramp up and ramp down time. So again, delay is not really taken care of. I think in the main, what you can say is that the new waveforms, alternative to FDM, what they achieve is to have lower out of band emission, more or less. Okay, you can say that's the general property. Some more, some less, but that's what more or less all of them claim. And because of reduction in the guard time, or really removal of it, they also improve the bandwidth efficiency. Okay, so these two facts are there, and then, you know, some other minor implications. Now, not everything is for free. For example, I'm not too aware of research in GFDM and MIMO. I don't know, Sashank, if you can comment on this. There is, but it didn't start to be compatible. Okay, so but it didn't start very long ago, I suppose, right? It's like probably last.
It has a problem because of self-interference.
Correct. So exactly. So there is something starting in GFDM application to MIMO. There is definitely some work in filter bank. My group is doing some application to MIMO. Actually, in filter bank, though, it's more tricky, because historically filter bank has problems with MIMO. Filter bank has never. It's a very old technology, even older than OFDM, I think. Or, you know, they're definitely both old. GFDM is 2009, I think, newer anyway. So filter bank has some problems with MIMO. Okay, I don't go into the details, but it doesn't fit very well. So what we found is that if you have massive MIMO instead, it's fine. Okay, but you see, you cannot say I propose a new waveform, and on top of it, your system has to go massive in terms of number of. It's too much to ask, right? So the natural evolution would be that you show that your waveform is compatible with few antennas, right? You don't want to change everything in the system. It's not even realistic to ask. So there are people working on solutions, but my main message here is that you will need some MIMO capability, period. And if your waveform doesn't fit with that, you have a problem. So Houston, we really have a problem here, because it's not so straightforward. So we go back to dear old OFDM, which has no problem whatsoever, has been working forever with MIMO, massive MIMO, easy extension. You just do your signal processing for per subcarrier. So you do your MIMO design, one subcarrier, single carrier, many subcarriers, you don't care. It's always the same thing. You copycat what you do per subcarrier, period. Cyclic prefix takes care of other impairments, works. Okay, so my main message here is, again, you see, when I said yesterday to be open-minded, it didn't only mean open-minded towards the future. That's kind of a given, right, for a researcher. You also have to be open-minded towards the past, because a lot of smart DSP has been going on, and many things work, right? And OFDM has been a fantastic technology. It has been the base for 4G. It has been the base for WiMAX. It has been the base for quite a few Wi-Fi standards, digital video broadcasting, digital audio broadcasting, and I'm forgetting some. Okay, so it has been universally applied, and it's been a huge success and a very good idea. So if you want really to replace it, there has to be a very good reason, right? And of course, research, you can be free and you can try things, but when it comes down to engineering, we also have to be aware that what we do has to have a practical application. Right, so papers are fine, and we need those for PhD, but eventually we have to keep in mind that has to be used at some point. So my message, again, is a recurring message of this course. Ask yourself why. How? Piece of cake. You got your books, you got your software, you got the mathematical, I mean, I'm exaggerating, of course it takes effort and it's not easy, but it is something that you will get eventually, right? You work hard, you talk with your advisor, you talk with your colleagues, you travel, you attend conferences, you know that this is going to work out, right? If you have the right mindset and the right commitment, it's going to work out. More difficult is to find out the why. In my experience, that takes time. So you will probably understand why you did what you did during the PhD a few years later. Might sound crazy, but that's normally what happens, okay? So, and that's when this understanding of the why kicks in, then you are a mature researcher. In a sense, PhD is not enough, okay? It takes a bit of years, and then you're ready to start your own research team, in a sense, to be a leader in your technology field, okay? Until you don't understand fully the why, then you're still learning, okay? So it will take a bit of time. So ask yourself why you do things, okay? So it's not enough. I mean, if let's say I'm examining, sometimes I do examine PhD students, right? So, and normally they know all the nitty-gritty details. They can swamp me with equations. They will probably be much better than me in their specific topic of investigation in terms of math and technical details. But normally they struggle when we go into this kind of discussion. Why the heck should we bother, right? So FDM is there, it works. So unless you convince, I mean, there are some reasons. Now we're going back to that. But unless you're very convincing about that, nobody will listen to you, right? Because new waveforms, new phi schemes, they cost half a dime at the tech market. You can go and you buy as many as you want, right? So, but you will be successful when you really convince people, and I don't just mean academia, I mean industry, I mean government agencies, I mean regulators, that what you do is indeed needed, okay? Otherwise, it's an intellectual exercise, and it stays that way. Yes?
The waveforms that we actually we will be using for 5G waveforms, there is one more requirement in low latency of operation.
Correct.
So the current waveforms, if we say, like as you mentioned, GFDM, if I remember correctly, it has a problem with the latency.
I think GFDM probably the problem comes from the fact that you process things in batches, right? Yeah. You have a super symbol in a sense, so it's multiple times symbols, right? And then you have like just one cyclic prefix for all that. So I think, in fact, I don't think GFDM is probably going to be the right.
It might not be used for low latency of operation.
Right. I think, yeah, I read actually the paper that they were claiming that single carrier could probably be the option.
Yeah.
Right. So again, it's not for sure that you need always like high data. I mean, multi-carrier is good for high data rate, I think. But if you have applications that are more focusing towards low latency and they don't care too much about throughput, single carrier might be the option. In fact, many of these machine type communication, they focus a lot on responsiveness, right? Few bits to be transmitted, but it has to be quick. And the de facto standard at the moment is GSM, right? 2G. So again, be open-minded towards the past. I think probably still there are scenarios where you do need to be quick and high throughput, then I don't think single carrier would do the job. So probably we'll need some of these new waveforms, in that situation. But
Yeah, there is something it's called tactile internet that is also
correct,
there.
that's from FedVoice.
It has to be also less, and the data rate also has to be higher.
Correct.
If you consider like 3 viewpoint videos and all.
Right.
So there both the requirements also to be there at the same
Right. Then I don't think single carrier would do the job. Right. Then you need a better way to do multi-carrier. Okay. Think there are.
In that case, probably WebDM might stand out in that sense. WebDM still has low latency of operation.
Correct. I think though the OFDM has a big issue with synchronization, right? So, but for example, if somehow you could sort that out, then OFDM would stand a chance. But I think if you really want, say, I don't see this as a common approach in research. Normally people don't think OFDM is going to work out, but if you would want to stand a chance with OFDM in these new scenarios, you would have to sort out the synchronization problem. You see, another problem I think is the burstiness, right? So you transmit now and then, and there is a machinery like in place with OFDM that requires like a lot of exchange of communication in the beginning of a frame to synchronize, right? And if you just transmit very little, it's not worth it. So better you have a sloppier, if you want, system which has non-orthogonal subcarriers like filter bank or GFDM, where things are quicker to set up. So again, but then you have the batch processing in GFDM, you have the ramp up and ramp down in filter bank, so it's not for free. You do have delay issues there too. You do have latency issues there too. The truth is, it's a very rich research space. Okay, there's a lot of work going on. I mean, my suggestion for those of you that are looking for a topic or maybe starting to work on similar topics, you have to find a way to distinguish yourself, right? So if you say I'm doing work on waveform X, my answer will be who doesn't? Everybody's doing that, okay? Or I'm doing work in massive MIMO, good luck with that. Everybody's doing that. So you do have to find some combination space. I mean, for example, combining one technology and another, or focusing on a specific vertical market, right? So you have to find a way to distinguish yourself. So your research problem should not just be technically challenging, should be also, like, in a sense, almost a landmark of yours, right? So it should be an advertisement for your future research career. So you have an easier chance, I think, when you kind of intersect research spaces. So either if you want to stay in PHY, different technologies combined, or maybe targeting different requirements, or if you want to work more at resource allocation system level, to try to see the impact the technologies have on the deployments, on the system throughput. It's something I'm very interested in with my group. So we're trying to pick technologies and see, how you mix and match them, how you pick and choose. So is it better this guy or this guy? How do you pick? Which scenario? Is it density? Is it mobility? Is it latency? And what if you combine them? One thing I learned in my career is that combining technologies doesn't necessarily add up. Things might go against each other, or things might be redundant. One example is if you want to increase the data rate, well, you don't necessarily need MIMO. Maybe you can just reduce, increase the coding rate, right? You decrease redundancy. So if your channel is trustworthy, that's all you need to do. Or you pump up the modulation and coding rate. So it's not like that. You need always the most complicated setup, and So you do need to see how the things combine. And I think the question is, how do you choose? Okay. So if it's always going to be better to use one technology, what I'm saying has no point. But if there are situations that are more of a trade-off nature, then that's where the interesting problems are. So try to also identify trade-offs, right? So throughput versus coverage, or throughput versus coverage versus delay. That's where the interesting problems are, I think. Okay, D2D, that has been there for some time, right? Device to device. Again, it's an alternative to, or you could integrate it with things like ultra dense networks or Wi-Fi integration. It's a way, in a sense, to cope with the surge in capacity. So the cellular networks cannot make it anymore, so they need some help. So either you deploy another layer of small cells like heterogeneous networks do, or you basically possibly offload the traffic to some alien system like Wi-Fi, or you might actually transfer the onus on the communication to the users. Okay, so if there is some local need of content distribution, you don't necessarily have to go back to the base station and the core network all the time, right? So there is a lot of work. I mean, it's not exactly what I'm showing here, but it's relevant. It's like local caching. People working in networking, they will probably be more familiar with this. So you don't necessarily need to have everything like a tree structure, right? It can also be that the leaves can communicate themselves, right? So if you do need if you do have some community of users, why do you have to go back to the base station? Imagine, for example, you are working in this classroom and you have to exchange some information about the course. Why should you go back to an access point? You might just be able to arrange it yourself, right? So of course there are issues with power, right? So the problem with mobile phones, the power is low, so it has to be like limited range. There are issues with coordination. All of these, right, links somehow have to find out by themselves what to do. So it's more of a distributed setup. But there is it's definitely an interesting problem, and it's in the research agenda of 5G. Yeah, integration with Wi-Fi. I already said a few things. The main message here is that you don't necessarily have to waste everything that has been done before to dump it. You might use it to your advantage. Okay, so and possibly Wi-Fi is one such thing. So if you have a surge in capacity, you just make sure that your users can seamlessly attach to Wi-Fi access points, right? And then they get back to your network when the problem is over, for example. I think this is more of interest, in fairness, to industry than to academia. Okay, I don't see an awful lot of interest in academia about this, but definitely telecom industries are very interested in this problem. So it's maybe more of a business problem, but relevant nonetheless. Massive MIMO is really one of the giants in a sense in 5G. There is no talking about 5G. I wouldn't mention massive MIMO, so it is going to be there. It might be combined with millimeter wave because you can put the antennas closer together because of higher frequency. Might not. I mean, I think since you are basically not assuming multiple antennas at the mobile phones, only at the base station, you have the luxury in a sense to deploy a lot. Okay, so even if you are at lower frequencies, say 2-3 gigahertz, probably not a big deal. Once you sort out the real estate problem, right, you have your own tower, then you can do whatever you want. Okay, there are issues, of course, to do with complicated signal processing, with complexity and so on, right? It's already difficult to do MIMO. Imagine massive MIMO. So it's going to be definitely a challenge in terms of engineering. I think RF engineers are normally very cautious about talking about massive MIMO. Somehow communication theorists and signal processing guys are more enthusiastic, but when I talk with RF people, not so thrilled, right? Because it's a lot of work for them, right? To write an equation or to run a simulation is easy, but when you have to to fabricate the device, it's another story. So I think eventually it will happen, but it does require some more RF engineering, I think, to be sorted out. The advantages are more or less the same of MIMO, but just scaling up, right? So you do have a boost in the data rate, you do have a boost in the energy efficiency, for example, right? A big thing is that SNR can really be increased a lot, and another big thing is also that this is enabling a lower inter-cell interference. What I mean is that because of the very high number of degrees of freedom in space, you can basically create what we call pencil beams. So beamforming really to the extreme. So it's almost a line, Okay, theoretically would be aligned with an infinite number of antennas, but practically it's very, very thin, very, very narrow, the angle, so you are just transmitting to your user. And unless the receiver of the other system is really aligned with you, which is unlikely, you will not interfere with other cells. So is that all good? And every problem is solved? No, of course, never is the case. So the problem is that you do have issues with what we call pilot contamination. So again, the advantage of massive MIMO, reduced interference in terms of the radio access. Another good thing is also that you do increase the spectral reuse, because if your user is, like if you transmit to your user very directionally and the user is nearby, you won't feel the interference, right? So because you're really transmitting in a very precise way. Then you create another beam to the other guy, and unless they're close, they will not disturb each other. So they can use all the spectrum, right? You don't need to do frequency separation of any sort. So in a sense, the problem of resource allocation and scheduling becomes almost irrelevant. So there are actually some paper claiming that this might be the end of MAC. It's not the case though, because you do have issues with the way you estimate the channel. What happens is that you still need to do channel estimation, right? Say basically you allocate pilot sequences to your users, they transmit, in uplink you estimate the channel. The issue is you cannot basically coordinate between cells because of coherence time. You have to, in a sense, do it in a self-contained way. Every cell has to find out by itself which pilots to use, and then other cells will do it. You have a limited set of pilots, okay? And what happens is that invariantly there will be a clash. Probabilistically this will happen, right? If I have a set of 5 pilots and Kartik has a set of 5 pilots and so on, it might happen that users that are that some users pick the same, right? What happens is then since you're transmitting practically the same pilot, there is no orthogonalization, so your base station will receive some of my pilot signal and vice versa, right? So that's what we call pilot contamination. And so the main message, I don't want to go into details, but the message here is that you just move the problem somewhere else. So you don't have the problem with the radio access, but you do have it with the controlling sense, right? So radio source allocation is not that with massive MIMO, it's just moved somewhere else, okay? So there are actually works, even in game theory, we do have a work, since yesterday you heard about game theory, we do have a publication like this year on how to use game theory to solve these issues. There are many, many work. We have another work focusing more on physical layer solution, okay, to pilot contamination. So it's definitely an active research field. It's getting a bit saturated, honestly, because people have been working a lot on this, but this is probably the single biggest issue in massive MIMO. Okay, that's interference alignment is just another advanced MIMO scheme. I didn't work on this, so I will not comment too much, but practically the idea is that somehow you pre-code your signals in a way that you say, if you are the green guy, you try to make sure by doing some joint transmission that the interferers will be in a smaller subspace. So in a sense, they will not mess up too much your transmission. Okay, I don't go beyond this. If you're interested, there are papers, especially from Professor Heath I think if I'm not wrong, is in Austin, right? And so this is also an active area of research. Again, I would say this was very popular a few years ago. A lot of work has been done. Maybe the issue now is more how this impacts system level, I suppose, than the actual design. But you might look into that if you're interested. So again, there are many things we can do. Okay, so you can use massive MIMO, you can use densification, you can use millimeter wave. You can do many things to solve many problems, right? You can solve the problem of having a lot of devices communicating, to be very, very reliable in communication, to have D2D enabled, high data rate, and so on and so forth. And normally, in my experience, the approach is never abrupt. Okay, engineering, as you know, it's an applied field, so nothing is abrupt, right? It's not that there is all of a sudden. I mean, sometimes it happens, but it's normally not the case that the new set of technologies will completely replace the old ones, right? Normally, it's more of an evolutionary approach. So you kind of gradually evolve from what is available right now to the new system. I think that is likely to be the case also for 5G. Definitely, it was the case for 4G. Okay, yeah, there was a big change in the sense that the access scheme changed in 4G, but other than that, many things stayed similar. There was an IP based communication more than before, definitely much more. But again, in the main, there was not a huge difference, okay? And that's why the main cellular system nowadays is called LTE, which means long-term evolution, right? So the industries at some point, they were a bit tired to change everything every 10 years, as they did before, and they kind of set out a plan to be sustainable, right? In terms of investments, in terms of technology, you cannot reinvent the wheel every time, right? Of course, you have to solve new problems to make networks better, but you have to build as much as possible on the existent. And that's the case, I feel, also for 5G. On the other hand, there are many new things that complement 5G. There is integration with Wi-Fi, there is new IoT applications, new technologies, of course, new access schemes we discussed before, new multi-antenna techniques, new bands, new architectures altogether. So, things will change, but I do believe that the technologies that will be successful are the ones that can integrate more easily with the current system. So again, you can write all the papers you want, but if you want your technology to be adopted, you have to talk the language of industry. Okay, so you do have to propose things that are reasonable. So, for example, massive MIMO is having a good fortune within industry because it doesn't imply the upgrade of every single device. It implies the upgrade of base stations only, right? And it doesn't have to be massive from one day to another. You might go from 10 to 20 antennas, for example. You still gain quite a lot, right? So it has to be a bit gradual. One issue I saw myself talking about waveforms with companies, they're cold, okay, honestly. Research has been going on and, everybody's talking about it. But when you talk to a manufacturer, that would imply they have to change everything, right? Because it's not that you can change it at the base station and the mobile phone, they won't talk to each other, right? So you do need to change both modulator and demodulator. Yes, okay. I think for segments of the network that weren't there before, okay. So if you have a new application, say a new system targeting new smart transportation, whatever, then I think you have the freedom, right? As long as you provide some interoperability with the system. But if you pretend from one day to another all smartphones will become filter bank instead of FDM, I'm sorry, that's not going to happen, okay? So you have to be aware also of the reality of things, okay? The reality of things is that we have to talk to industry, and they're the ones really driving the process. So unless you convince these big bodies like GSA, 3GPP, and so on, that your technology is worth its salt, it will stay a research paper. Okay, that's being very blunt now, but I think that's the truth. Okay, so you have to have keep an open mind again towards other sectors. It's very important for your career to be intersectorial. There's been a lot of talk about talking about interdisciplinarity, even too much. Honestly, it doesn't mean much eventually, right? So interdisciplinarity means you have to talk with people from other disciplines, use their tools, they have to talk to you, and sometimes it works, sometimes it doesn't. Okay, that has been done. An example is game theory. Game theory is originally not a tool that was invented in our field, but it has been applied to a great and successful extent. What I see a bit less in academia is the intersector approach. So you have to really talk to companies. We have. I mean, I'm also blaming myself now. We have to talk more to companies. So I'm trying to do that more myself. So I encourage you. Now, depends on the stage of your career. Maybe PhD is not the best time to do that, but at some point you will need to discuss more. Otherwise, you know, the risk is that you do very good work in research, but the main risk is that it is irrelevant, right? So you want, at least I want, my work to be useful to the community and the system, right? If it stays in a research paper, yeah, intellectually satisfying, but that's it, right? So you do want to take it out there. So you do have to have an intersectorial approach. You have to talk to companies. What are the real problems? It's not the problems we come up with to have a nice formulation. What do we need to solve, okay? What is viable? So between a technology that is super fantastic, that will never make it, and another that is maybe stands a chance from commercial viewpoint, I would encourage, you know, to have a preference for the second, right? You can still do a general theory, and so you can have both in a sense. Okay? You can do your nice math, and so I do myself that, but you should also keep an eye on practical problems, right? And practical problems are the ones that industry considers to be practical, not us, okay? Another issue, which we'll go back when I'll start to talk about spectrum in the afternoon, is regulation and policy. You can come up with a fantastic solution from the scientific viewpoint. It's even implementable and the companies are happy with it. But if you cannot use the spectrum to do that, or you know, it implies an excessive interference to some existing systems, the regulator will shut down your system the day after. You see, so it's kind of a triangle. So you do really have technology, which we always talk about. You do have industry, which sometimes talk about. We have regulation, we never talk about it. So you do need to keep in the loop all these three actors, right? So you do have the science and technology, you do have the business, but you also do have the regulation and policy, right? Because eventually it's the authority for telecom that decides what will transmit over the air and what won't, right? And so if you don't consider that in your system, you are in trouble. For example, in terms of business, it wasn't really well planned by industries. 3G. 3G was designed according to engineers' wishes. People didn't need 3G at the time. Okay, so it was a big flop. I think 4G they did a better job, but they kind of put too many things in mobile phone that people didn't really need. So that happens, and there are gigantic flops commercially when you don't consider any of the terms of this equation. So technology, yes, but also, you know, industry, industrial relevance and business, and regulation and policy. They are all very important. So again, just to close this lecture, we do have a trend towards increasing deployments in 4G and 5G. 4G is pretty much getting to a stable. You see, it's like now we are more or less here, so it's kind of close to reach a plateau. Early 5G and fully 5G, the difference is that early 5G, I think they consider in this study 5G without millimeter wave. So 5G is sub 6 gigahertz, and fully 5G is including the millimeter wave bands. And you will start to see some early deployments from next year, possibly. And then I think millimeter wave is supposed to come about in the beginning of the next decade, but it will still be, you know, pretty much growing for a while. So if you compare with the other curves here, you might have to wait until, you know, 2035, 2040 before the 4G reaches, before the 5G reaches, let's say, the plateau. And by then we will have at least a couple more of generations being researched upon. So it's really a very evolving field. Okay. Still, I think at least a few years ago, GSM was the most used system in the world. I'm not sure if it's still now, but so just to tell you, it's not that 2G is you know, in the dustbin of history. It's still there. Okay, so things will stay for a while. So that's very important then to you know, cross all the T's and dot all the I's when you design a system, because it's going to stay for a long time. So if you screw it up now, there's not much way back, right? It's going to be screwed for another 30 years. So it's very, very, that's why people, like companies especially, are very cautious about adopting new technology. So if you want to stand a chance, you have to convince them. And you won't convince them just with equations. That's the take-home message of the lecture. So see you at 3. Okay, any question? comment? Yes, Asham.
Researchers are also talking about these novel multiple access schemes. So
Yes.
how about that? Is it relevant?
So can you make an example? Just to
MoMA?
I think it is. We are not doing exactly work in my group, but I know there's been like this non-orthogonal multiple access.
Why was working on why people
I think it's probably the same reason why they want to get away from FDM, right? To get rid of some of the. It's not maybe synchronization in that case, but in a sense, it is, right? It's like instead of being within subcarriers, probably within users. So I think a big deal is with requirements in terms of synchronization. So if you have a very dense environment like many sensors, it's very difficult to ensure that they are, synchronized between each other. So when they access the medium, you invariantly will have some multi-user interference. Okay. So one way to get rid of it, for example, is also massive MIMO. With massive MIMO, the more antennas you have, theoretically, multi-user interference vanishes. So I think they were trying to relax. I don't know too much about that.
in MoMA they are just trying to increase the spectral efficiency.
Yeah, but that's
They
what.
are using the same resource for two users.
Correct.
Time frequency resource.
Okay.
They are using the different power regulation.
Okay, but I think in spirit it's probably similar to what you try to do with GFDM or BMC, I suppose, just focusing more on the multiple. I don't know the details of that technology, but I guess it's about relaxing the requirements on multi-user synchronization. I guess at least to my understanding, it's not really hugely popular. Now I don't work all my time in Phi, so there are better people than me that can tell you about that. But to my understanding, it's not one of these things that appear in the 5G wish list. Okay, there is work, yes, but it doesn't have the popularity of new waveforms, massive MIMO, dense networks. Definitely not. Okay, so it might be still going to be. It might still be picking up, but I don't think it's so successful at the moment. Okay, that's the high level. But yeah, there is work going on. Any other question? Yes.
Actually, you are telling about this high spectral reuse is possible. Massive MIMO that by efficient usage of the spectrum.
Yes.
Can you tell me that spectrum? What are the spectrum they identify in 5G?
Yes. Well, essentially there are a few things happening. So the question is about the spectrum bands of interest to 5G, right? Basically. Okay, of course, anything we are using right now, right, is going to be used. So 4G bands, like say around 2 gigahertz, for example, this is going to be there. Other bands that are being considered, let's say, when I say 5G, I really mean 4 to 5G, right? We are in the process. Another set of bands, it's 2.3, 2.4 in Europe. It's used for this new spectrum sharing system, which is called LSA, License Shared Access. So, for example, it's bands used by wireless microphones or by these news crews that are transmitting, news, for example, like these systems, and then missile tracking in France, for example. So there are some activities there. There is activity going on in 3.5 gigahertz in US, which is again mostly used for radars, especially naval radars. And this is going to actually the Federal Communication Commission, FCC, suggested this to be used in coexistence with small cells. Integration with Wi-Fi is relevant, of course. 2, 4, and 5 is there. Few radar bands in the sub 6 gigahertz band. Millimeter wave, normally they consider 28 to 31 and 60. There are actually some countries that have sold the bands that were freed by TV white spaces, right? When they moved to digital TV, these bands became available, and they're very good. So we are talking 400 to 700 megahertz. For example, in Brazil, they were bought by LTE. Okay, so there used to be a time where these were considered to be of interest to wide radio area network, like cognitive radio networks. This 802.22 standard. In my opinion, that has not really gone very far, and it's now being acquired by LTE. So LTE means also 5G later on, right? So So I think it's pretty broad spectrum. There are people talking even higher.
38 against 72.
Yeah, there is a lot going on, and there are people talking even beyond, right? Like where they really want a terahertz of spectrum, terahertz, and then you have a gigahertz of spectrum, something like this, right? So it's a lot. Okay, so there is a project I heard about in ICC 2013 about these super high frequency. So there is definitely research going on. My only take is that it's already difficult to do millimeter wave, so it's going to be even more difficult to do that, but there is work, definitely. And I suppose if you have very short range applications, right, you can enforce line of sight. It could be used for super high transfer data, right, kind of super Bluetooth if you want, I don't know, but it's not still, I think 5G is not that brave yet. They don't go beyond 60 gigahertz, okay? So yeah, so it's definitely quite large, the domain of interest. Yeah. Any other question?
So you were talking about Sawi network.
Yes.